Well, I am glad to be. Uh-oh. Is that too loud? It's all right. So I am glad to be here. And I was actually supposed to be Dennis who was here, actually. Dennis Sullivan and I were both asked to come. And he was going to come, and I was going to stay home. But he inconveniently won the Wolf Prize. And that meant he had to go to Israel to collect that prize. So I said, okay, I would come. I will be talking about work that's joint with us, between us. I've labeled this the roots of differential cohomology because at least one root of it, and maybe a main root, started with work that I did with Chern in the early 70s, where we try to make some hay out of these forms up in the principal bundle of a bundle with connection, these forms, D of which were the lifts of the various characteristic forms. Chern's original work, when he gave the beautiful proof, his beautiful proof of the Gauss-Bonnet theorem, he lifted this Pfaffian form up to the sphere bundle, observed that up there it was exact, but the particular form of which made it exact had virtues, and in particular its integral over the fibers, the spheres, were integers, and that allowed him to give a very elegant proof of the Gauss-Bonnet theorem. So he and I did some work in this area 25 years later in the early 70s, and we're able to find various applications of these forms and get some numbers out of them and so on. But it was a goal that I worked on with Jeff Cheeger to try to bring these things down to the base. I mean, there are forms upstairs, but somehow to get them down into the base. So I'm going to give an example, which I hope won't be too complicated to read. So we'll start with a Hermitian vector bundle with a connection theta and curvature omega, and we just look at the associated frame bundle. So this is n minus k frames in this vector bundle, and the fiber is a unitary group modulo uk minus 1, and there's the total space. So if we look at the integral Chern class, the kth integral Chern class, it can be represented via the Weil homomorphism. Well, it could be represented by a form. It is the Weil homomorphism downstairs. But the way I've indexed this, when you lift that form up to this bundle, it's exact. It's D of what we'll call TCK. So that's because when you lift the whole thing up, there's no obstruction. So the Chern form becomes exact, and this form here, TCK, is basically a canonical form, at least up to something exact. So there's a formula for it, you could write it down, but it's canonical if you want to make it natural. So here are some virtues that these forms have. First of all, this has integral class. Integral periods, when you restrict it, it's closed if you simply restrict it to the fiber. And it has integral periods there. So now there's a standard exact sequence of this picture which sends the 2k minus first homology of the fiber into that of the total space, and then downstairs. This is exact here, and it's onto, as indicated here. I don't think this is necessarily an injection, but it doesn't matter. So here's this exact sequence, and from that we're going to get a number a function on cycles, so downstairs. So here's gamma, it's a cycle downstairs, a singular cycle, and pick something upstairs, a cycle upstairs, which pushes down to something homologous to gamma. Now you can do that because this is onto. Because this map is onto, there's something upstairs that pushes down to be homologous to it. And we'll just call this function ck hat of gamma will upstairs integrate over this gamma bar, the cycle upstairs, this TC form. We'll integrate that, and we'll sort of correct that by integrating this, the Chern form itself over beta, over the interior of this thing. And we'll reduce the whole thing modulo the integers. Now, these integrality conditions and exact sequences guarantee that this is a well-defined map from cycles into R mod Z. All the ambiguities they're all integral, and they're taken care of by this condition, these two conditions, that these are both have integral periods. So this is a well-defined function of cycles on the base. So that's an example. That kind of example is what led us to define what's come to be called differential cohomology. We call it differential characters, and Jeff Cheeger and I did this in 1973. So formally, we have the category of smooth manifolds with corners yet. Zi of x are smooth singular cycles. If we have a real cochain, we're going to regard, if we have a differential form, we'll just regard it as a real cochain for the moment via integration. And anything with a tilde over it is reduced mod Z. So then we'll define this group. It actually turns out to be, well, it's a group. HK hat are functions which are homomorphisms of the cycles, in this case k minus 1 cycles, into R mod Z, with the property that on a boundary, it's the reduction of an mod Z of the integral of a form. So this is a very, very simple definition. You would notice, if we had the previous screen up, that this business about on a boundary being an integral of form, that came right out of the formula. So in the previous example, on the boundary, it was simply an integral of that Chern, the appropriate Chern form. So if we let Z, wedge KZ be closed forms with integral periods, it turns out that this form, omega, is actually uniquely determined. There's only one such, so we can call it omega sub f. F was the original differential character. It's uniquely determined. It happens to have integral periods. It has to. And by a Bachstein-like construction, which I won't go through, it also determines an integral cohomology class. So it determines more than just a differential form, which would represent a real class. It actually gives you an integral class. And the relation between the form, which is closed with integral periods, and the class is that the real image of the class is represented by that form. So this is a pretty simple setup. H1 is just C infinity maps into the circle or into R mod Z. H2 turns out to be isomorphism classes of U1 bundles with connection. And in that case, this function, in this case, is simply 1 over 2 pi times the log of the holonomy. So if you have a closed curve, you can consider its holonomy. This is just a U1 bundle. You can take the log of that. It's just an angle. And that's what this is. And omega sub f is the curvature. And mu sub f is the integral Chern class. So holonomy you usually think of as going around closed curves, but you can actually just make a holonomy function around cycles. And it'll work just fine. So this gives you all this information. So those are examples of these things. Now, this whole H hat turns out to be a graded ring. You can multiply two of them. I won't tell you how, but you can multiply two of them, and it's a canonically defined multiplication, and it's graded in the obvious way. And so when you go through all that, you get this diagram, and the diagram is really what tells the story. The diagonals are exact, so let's look at one diagonal. Let's look at this one. So here's HK. Now going into it is R mod Z cohomology. Well, that's functions on cycles. You can think of R mod Z cohomology as functions on cycles. In fact, it's independent. It only depends on the homology class of the cycle, but nonetheless, that injects into here, and that's the kernel of the map that into omega sub f. That's the kernel of the map of H into this forms with integral periods. So this is an exact sequence. Here, this is forms themselves modulo forms with integral periods, k minus 1 forms. Well, how does that give you a function on cycles? You just integrate the form over the cycle. And then, of course, something with integral periods is going to give 0, so that doesn't matter much. And that is the kernel of this homomorphism that we described into the integral cohomology. So these are two exact sequences. This is the coherence statement that I said. The integral class is represented, the real image of the integral class is represented by the de Rham class there. And over here, odd real cohomology obviously maps into R mod Z cohomology. By de Rham, it maps into this picture and this commute. So this is a commutative diagram. And all the maps, it turns out, are ring homomorphisms, although we've just put in this particular grading. So this is the sort of iconic diagram that represents differential cohomology, no matter what it turns out cohomology theory we happen to be using. So, which we'll get to. So with that, it's reasonable to ask, well, what extra information are we getting? I mean, we have an integral class, we have a form with integral periods. Is there anything more? Maybe it's just those two things are enough. But so let's look at pairs where an integral class and a form where one where the de Rham image of the form is the real image of the class. So that's what we're getting from those two maps, mu sub f and omega sub f. So if we map HK into that, first of all, it maps onto, and second of all, its kernel is a torus. And the torus is of dimension the k minus first cohomology, so the real cohomology. So this does provide more than this, and it's not simply, I mean, it doesn't simply break up as the product of this torus times that, although it does point set-wise, but not algebraically at all. So that's the extra information in these characters. Not much, a finite dimensional torus, but it turns out that there's a lot of information there. So, okay, let's go on. Now, a wonderful thing happens. The Weil homomorphism, the famous Weil homomorphism, factors through this setup. So if you have a principal G bundle and an invariant polynomial in the Lie algebra, such that omega sub p, that's the, W of p, that's the Weil image, universally represents the real image of an integral class, then we can define a natural element determined by both of those in h hat of x, with the first delta of that equal to the form and the second boundary map of that into the integral class. But there's more to it because there's that torus floating around. So the Weil homomorphism has a lift, and that lift is natural, canonical, and all the rest. So now, roughly at the same time that Cheeger and I were doing the stuff I just showed, or defining that stuff, Deligne defined Deligne cohomology in a completely different setup from a different point of view. But if you look at it in the smooth category, this is Deligne cohomology. So it's pretty interesting that two different groups working from very different points of view at roughly the same time came up with this construction. Now, this has been useful in proving some non-immersion theorems, in proving some, looking at some flat bundles and various things. So this has been quite a useful construction, and of course, the physicists liked those forms, those Chern-Simons forms. We heard about one of them this morning. And gradually, the physicists have been looking at these characters. So I don't know very much physics, but they seem pleased with the notion. So before we get on to that, so this is some work with Dennis Sullivan. So I showed you that iconic diagram. Now, Blaine Lawson and others started constructing quite a number of examples of differential characters, constructions of differential characters, all of which led to the same diagram. So it was reasonable to ask, does the diagram tell the whole story? And the answer is, as a functor, H hat is indeed uniquely characterized by that diagram. That's not a trivial result, but there it is. So if you have a functor on that category, C infinity manifolds with corners that satisfies that hexagonal diagram, there is one and only one up to a natural transformation, and in fact, it's a unique natural transformation. So that's great. It's essentially axioms, if you like, for that functor. Now, in 2005, Hopkins and Singer wrote quite an important paper and showed that an H hat-like thing can always be found corresponding to any cohomology theory. And such functors are now sort of called differential cohomology. H hat is the ordinary type. So now we're going to talk about K theory, and everything following is joint with Dennis Sullivan. So first, I have to give some notation. So wedge BGL of X is going to be the ring of total even closed forms that are cohomologous to Chern characters of complex vector bundles over X. So that's kind of a discrete family of forms, because complex vector bundles are discrete. It's not a continuous family. That's what BGL is. So it's a total form. It's not just a single form. And that takes the place of the forms with integral periods. That's another type of quantization. Now, GL will be the infinite general linear group. And on that group, there's a canonical Lie algebra valued 1 form, which is just a sum of the trace of odd powers. I think that's supposed to say 2j minus 1. That's a 2 there, if you like. So this is a sum of the trace powers with coefficients, and these are the coefficients, not where it comes from, but it's, in a sense, this is the universally transgressed form of the Chern character. But in any event, it's a closed form. Yeah, it can be thought of as a transgression of BGL. And so we have that. And I want to define wedge GL as the pullbacks of such forms under maps of X into GL. So look at all maps of the manifold into GL, pull back that total form, and throw in exact forms, throw in all the exact forms. Obviously, if this is homotopic to the identity, the pullback would be an exact form. But just look at all that stuff, wedge GL. And that is, well, there it is. There it is. Now, this is what differential K theory ought to look like. So in the middle, we have K hat. Now, the map into cohomology would just take K hat into even dimensional K. And the kernel of that map that injects into here should be all odd forms modulo this wedge GL. In the previous case, it was forms with integral periods. It was odd forms. It was forms with integral periods. Now, again, this is a discrete family of cohomologically discrete. Well, anyway, that's what it is. It's forms with closed forms with this type of closed forms, wedge GL. So, and this sequence should be exact. Here, instead of even forms with integral periods, we get these forms which come from the Chern character, total form there. And this, well, this is odd-dimensional K-theory with coefficients in C mod Z. I'm doing all this over C instead of R in a way for simplicity. But whatever this is, that's going to be the kernel, and everything else is commutative. If you go, there's a Bach-Stein map in that situation, and this commutes, and there's obviously a D map. So a K-differential cohomology functor should be a ring-valued functor fitting the above commutative diagram. And so now the goal of the rest of the talk is to present a simple geometric construction of such a K-hat, and in the course of achieving this, we'll develop a straightforward analogy to K-theory for complex vector bundles with connection, something I'd always wanted to do. And the other is to gain an understanding of how much information about a vector bundle with connection is carried by its characteristic forms and characteristic classes. So, so we're going to make a construction here which will give an example of differential K-theory. So we'll start with a complex vector bundle with connection. Now we're going to call the connection del instead of theta, and we're going to call the curvature R, which is a two-form downstairs with values in the endomorphisms of the bundle. That's the curvature form. Ch of V will be the, in H even of X will be the Chern character. And here's the Weil homomorphism, so you can represent the Chern character as the sum of trace powers of R. So you can squish R together to take the trace. I think I've left out a 1 over 2 pi I factor here. I'm not sure. I forget. But I'm pretty sure it is. So if you're taking notes, put a question mark right there. And this is a closed form, and it represents the Chern character. And now, if you have a one-parameter family of connections, say alpha, here's the connections, delta up at T, smooth curve of connections, then you can look at its derivative, which is a one form with values in the endomorphisms of V. So you can just differentiate a family of connections, and you get a one form downstairs with values up there. And this CS form is something whose differential is the difference between those two Chern forms. The two Chern forms are obviously differ by something exact because they represent the same cohomology class. And this is a canonical construction for finding that. And this, well, it is. And CS is Chern-Simons. It is the kind of form that was used before. Here we're looking at this total odd form. And it turns out that if you have two paths connecting, the difference between these two is exact. So we can define then CS of a pair of connections, take any curve gamma joining delta 1 to delta 2, look at CS of that gamma and take it mod exact, and that'll be independent of the curve. So this is a CS thing. So it takes two connections upstairs and turns it into a total odd form downstairs. And the little calculus shows that to go from 0 to 1 plus from 1 to 2 is the same as going from 0 to 2. And we'll define two connections to be equivalent if CS equals 0. Now, remember, it's mod exact because it's defined mod exact. So it's an equivalence relation because of this. And we'll define a structured bundle to be a vector bundle here with a vector bundle over M with an equivalence class of connections. We'll call that a structured bundle, for lack of anything clever to call it. So, so that's a structured bundle. If I have two of them and an isomorphism covering the identity, two of them over X, I can pull the connection back, and it's easy to see that the equivalence class of the pulled back connection is the pullback of the equivalence class. So we can say the two guys are isomorphic if the pullback of one connection equals the other connection. So this is an isomorphism of bundles to begin with. So isomorphisms are well defined. If you have a connection over V, if you have two connections on V over Y, and we have a map of X into Y, smooth map, then it's easy to see we can, the pullback of the CS form is the CS form of the pullback of connections. So if you have a structured bundle over Y, you can pull it back and get a structured bundle over X. You can take their direct sum, that's all defined. You can take their tensor product, that's all defined. And by the way, it's clear that if they're equivalent, the Chern form of one equals the Chern form of the other, because remember their difference is D of something, and that something is CS of this, and if this is even closed, these two would be equal, but in fact, that CS form is exact. So Ch of V as an element of wedge BGL is well defined, and of course, it's easy to see that Ch of the sum is the sum of the Ch's and Ch's of the product. So that all that makes sense. So now we have now we've reduced connections into sort of a reasonable family of connections. They've maintained their character, they've maintained their Chern character, and they allow you to do the obvious things that you'd like to do. And we're now going to define struct X as the commutative semiring consisting of isomorphism classes of structured bundles. So just as perhaps Atiyah originally defined vect X to look at isomorphism classes of vector bundles, or someone defined that, we're just going to define struct X to be isomorphism classes of structured bundles. And it's a functor, as we've seen, on a category of manifolds into commutative semirings. Ch is a well-defined natural transformation, that map of the structured bundles into forms. Now, we're going to call a connection flat, capital F, if its holonomy is trivial. So thus, not only is R 0, which is sometimes flat or called locally flat, and V is isomorphic to the product bundle. So this is flat as a pancake. This doesn't have anything going on. That's a flat bundle, a capital flat bundle. And we'll just call an element a structured bundle flat if some connection in it is flat. And since any two such are isomorphic, we'll call this isomorphism class by bracket n. So that's sort of the trivial n-dimensional class as an element in struct X. Now here's a nice theorem. So if I have an element of V in struct X, I can find a W in struct X such that their direct sum, this should be direct sum. Those of you who are taking notes, needs a circle around it. V plus W equals N for some N. And W is called an inverse of V. Well, everyone knows that that's true for ordinary vector bundles. You can classify them by maps into the classifying space. That's one way to do it. And up there's two bundles, one and the inverses of each other. But it turns out, so what it means is you take the direct sum of these two bundles, and of course, each one had a connection, so you get a direct sum connection. You want some other connection, which you want to find some bundle with another connection, and then you want to put another connection in this direct sum, which is flat, completely flat, and equivalent to the direct sum of those of those two, and you can find such a W. And actually, this was based on something very similar that Cheeger and I stated without proof back before some of you were born, in all likelihood. So now, if you suppose you have a trivial bundle, and it has two flat connections. Well, I claim that the CS of that pair is actually contained in this guy. It's actually one of these fancy special wedge GL forms. And the proof is that by choosing parallel framings for each connection and expressing one in terms of the other, you get a map G of X into GL, just the matrix of transformation from one set of flat things to the other, parallel things to the other. And it turns out that the new connection, that the first connection, the second connection is the first one plus this, G inverse DG. DG is just the differential of that matrix valued map, so that gives you a matrix value in one form. G inverse is still matrix value in one form. And it's fairly easy to prove that this is that. And thus, CS of this pair is actually just a pullback of this form by G, mod exact. Okay, so you might hope that these two things were equivalent and CS was 0, but it's not quite 0. It's one of these guys. That's the way it goes, but that works out fine. So now, let's suppose that I had any connection on a trivial V, and I had picked two flat connections. So then CS of the first one against the flat one against the first one equals, well, by this chain rule, CS of the first one and the second one by that. And so that equals CS of the double bar one with the connection plus some element, this guy. So I can now define a map CS hat of any connection on a trivial bundle into H odd, not mod exact, but mod wedge GL. So if I have a trivial bundle and I want to, with connection, and I want to get a form out of that, I take a flat connection and I look at CS of the difference of the two connections. I say, well, what if I took a different flat connection? Well, the answer is that form would differ from the first form by one of these wedge GL guys, and so modulo that, I get CS hat well defined. So we'll have it. Now, I want to talk about not trivial bundles, but stably trivial bundles. So I'll define struct ST to be where the underlying bundle is stably trivial. You recall that means you can add a trivial bundle and the whole result is trivial. This is all topologically. So now, if I have, this is supposed to be ST. So I have V contained in ST. I'm going to choose two guys to trivialize it. So V plus F equals H. And I'll choose a flat connection on F. And now I'll define, again, CS of struct ST into this guy. So now I'm generalizing. I'm letting it be stably trivial. CS of V is going to be CS hat of this del plus this guy. This is well defined because now I have a trivial bundle, and this is a connection on it, so I can define that. But I can show that it's independent of the choices that I made. So CS hat really maps struct stably trivial into wedge odd, not just struct trivial. So, okay. So now I'll call something stably flat. This is all just sort of going by script. Call something stably flat if there's a flat F and a flat H with V plus F equal H. So obviously struct SF, stably flat things, fit into stably trivial things, so that goes in there. And now this is actually a non-trivial, somewhat non-trivial. So CS hat, remember, is mapping struct ST into these forms, and the kernel of that is struct SF. So the kernel of this map are stably flat bundles, and the image is everything. And that, actually, second fact, is kind of everything in what I'm talking about. So thus, CS hat maps struct ST, the stably trivial guys, modulo the stably flat guys, isomorphically onto wedge odd mod wedge GL. Now, one is fairly easy. This is fairly easy. I won't go through it. 2 is less easy. And it says proceeds inductively on K by showing that every 2K minus 1 form up to the element of wedge G can be realized as the CS of a direct sum of structured line bundles and the inverses of structured line bundles. So you do it by induction. You first show you can get 1 forms. That's easy. Then you assume you can get odd K forms, and you try to get the next one up, and you fiddle around with the line bundles and their inverses and use the induction, and it works. It works. So it's not obvious that this should be true, but it is. And that's gratifying. So now we'll finally define K hat of X as K of struct X, just like ordinary K of X is K of vect X. So it's the abelian semigroup of pairs, modulo V and W, modulo of a diagonal. That's one way of, that's this growth of deconstruction. And this becomes an abelian group. And as usual, elements can be written as the difference of 2 structured bundles in this case. And by the existence of inverses, we can see that every element of K is actually of the form of K hat, a structured bundle minus a trivial one. There's no relation between these dimensions. And one of these, a representative of this type is 0 only if the first one's stably flat and the dimension of V equals n. So this is a very good representation of everything in this, on this K hat. And it can be easily shown that tensor is well defined, and thus K hat of X is a commutative ring. So I have this K hat guy now defined as just a growth of decay of these structured bundles. Now, up here, Chush is well defined, and it maps K hat into BGL. That's a nice, ring homomorphism. And it maps K hat by just dropping the connection and forgetting about it into K even. So that's also a ring homomorphism. And that's what this, I guess this is what's saying. So both maps are ring homomorphisms, and this little piece of a diagram commutes. So if you take K hat and just map it into K even by forgetting the connection, and then look at the Chern character cohomologically, that'll be, you'll get to the same place if you take the Chern form and then use the Durand theorem. So this little thing commutes. So now, this del, it maps K hat, structured bundle K, into ordinary K. What's its kernel? And the answer is its kernel is exactly wedge odd modulo wedge GL. So its kernel is forms. It's just forms modulo that. And we essentially proved it because, first of all, before. So we'll let gamma take struct ST minus struct FS into K hat even by just taking a guy and V and subtracting off its dimension. So this gives you something, a dimensionless guy. You subtract off a trivial bundle represented. So that's an element of K hat. And by 1 and 2 in the previous thing, so I'll go back to there. By 1 and 2, that's an injection, not too surprising. But by the previous theorem, I could take I could take, see, CS hat inverse mapped here. We'll go back to the previous theorem for a minute. There. So CS hat took this into this. Now I'm going to take its inverse and go back. And I'll go back into, well, I'll go back. And that will give you this, this isomorphism. So therefore, it's the kernel of delta. So K hat even, structured bundles going into ordinary bundles, the kernel are these forms. And this is the injection that chushes onto, but this is commutative, is trivial to show, but that equals D, and that chushes onto comes from the fact that it's cohomologically onto, and it has all these things to work with. It has all the odd forms to work with, so D of it is going to give you everything. So now we're almost done constructing this thing. We have a diagram of functors. Everything commutes, except for this corner. We have something funny up in the corner. So here, this first exact sequence, we just sort of went through its proof. The odd forms modulo wedge GL sit inside K hat. That's the kernel of the map into ordinary K theory. Here we map onto wedge BGL. That's just a Chern map. And it has a kernel, so we'll just call it kernel of Chush. We'll just call it the kernel of Chush. And it's easy to see that but this is commutative. So I have the diagram that I wanted, except instead of having C mod Z odd K theory, I have this kernel of Chush. I have kernel of Chush, and I'm going to need to show that that's actually equal to K mod Z, C mod Z K theory, an object that probably few of you have encountered. But there it is. So, well, let's see. First of all, I want to show that kernel Chush is at least a homotopy functor. So that it's a homotopy functor gives you some confidence that it could be C mod Z K theory. Anyway, it could be some kind of K theory. Why is it a homotopy functor? Well, this is a lemma which is not difficult to show. So suppose I have a one-parameter family of maps from X into Y, and I have a structured bundle. On Y. So I can pull it back by this one-parameter family of maps and get a one-parameter family of structured bundles on X. And up to isomorphism, this actually leads to, you can fix the W, you can fix the bundle, and it's a one-parameter family of connections. So I have WT as a one-parameter family of structured bundles, the same W, and of varying connections. Now I want to know, what is CS of this pair, of the beginning and the end of this family when I pull back the first structured bundle and the one at the end of the loop. And here it is. You push over the parameter vector and take its interior product with the characteristic form, with the Chern character form of the target bundle. And you pull that, so that cuts it down by one dimension. You pull that back under phi sub t, and you integrate. You take the integral, you get all these forms back on X. You take the integral. So you push over the parameter vector, interior product with Chern character, and integrate, and that gives you the Chern form. And that is not difficult to prove. It's the only thing it could be. I mean, what else could this be? You have the Chern form over there, the Chern character form. You have a map, you got a parameter vector, interior product, you got an odd form that must be good for something. You pull it back, integrate it all along the parameter curve, and that turns out to be the CS form. Well, notice, of course, if Chush delta happened to be 0, CS is 0. And so if you were dealing with things in the kernel of Chush, then two things that are connected by such a one-parameter family. If these are both, if this is in the kernel of Chush and I have two homotopic maps pulling them back, I'm going to get the same answer. So not only as vector bundles, obviously, but also as characteristic bundles. So Chush is a homotopy functor. Now here's something that is, it's actually pretty important. So this is the Mayaviya-Torres property. So suppose that X is the sum of A, is a union of A and B with intersection D. And suppose that D has codimension 1. So D is fat. So it's just two nice things whose union is the whole space and with a nice fat intersection. And in fact, D has a column neighborhood in A and B. So in particular, a smooth form on D could be extended to either A or B. So I could draw a picture, but you get it, right? This whole space is the union of two spaces. Their intersection is codimension 0. It has an interior. And in fact, there's a column neighborhood into each one. So anyway, you can extend the form. So here's the Mayaviya-Torres property for K hat. So if I have a guy mu sum A in K hat of A, and mu sub B in K hat of B, and if their restriction to D are equal, if their restrictions to D are equal, then there is an element of K hat of X whose restriction to each of A and B is my originally given. So this says that, and by the way, this is true for ordinary differential cohomology, and I can show it's true for a very, very broad class of differential cohomology, the Mayaviya-Torres property. So these elements of differential cohomology are determined by their local behavior. If things fit together right, this is 2, but you can imagine you could do this for any number. But if it fits together, there's a global form. The Mayaviya-Torres exact sequence for differential cohomology does not, it's onto, if you know what Mayaviya-Torres sequence is, it's onto, that's what this says. Its kernel is skinny. Its kernel is skinnier than it is in the ordinary case. But nonetheless, it's true that, and importantly, it's true that, the Mayaviya-Torres property holds for differential cohomology, and then it's a triviality. And so that's not so easy to prove, although it's not too difficult. In general, it's a little harder. But so now the kernel of Chush satisfies the Mayaviya-Torres property as well, and that's completely trivial. If they agree locally and their characteristic form is 0, and they each 0 and they fit together, by the first theorem says, oh, there's something that welds them together. There's some universal character that restricts each of those. But of course, since each of those has vanishing Chern form, the big one has to have vanishing Chern form because the forms have to overlap and everything is 0. So the kernel of Chush certainly satisfies Mayaviya-Torres. So here I have this functor, kernel of Chush. It's a homotopy functor, and it satisfies Mayaviya-Torres. One can make fancy arguments to show that that object is going to have to be K of C mod Z. But actually, there's a much more direct way of proving that. In 87, Karoubi showed that K out of C mod Z could be derived from equivalence classes of triples, a vector bundle, a connection with 0 characteristic form, and an extra guy, a guy theta who's D of it. It was a kind of a clumsy construction. It was a triple. But nonetheless, and there was a relation, how you say 2 of these are equivalent, which I won't get into. And so you could prove it from this, showing that structured bundles are a subset of these things and so on. So it follows pretty fast from that. But you could get a direct proof from general topology principles, which I won't go into. So here we go. Here it is now in its full glory. This is the diagram. All the pieces fit together, and we do have H odd, ordinary over on this side, and H even, ordinary over here, and this guy sits in the middle. Mod Z is the map induced by the coefficient sequence. So there's whatever K hat C mod Z is, it always has a Bachstein map, and it has a map from C to C mod Z induced by the coefficient sequence. So this now is an example of a functor that satisfies what Hopkins and Singer say should be the canonical diagram for differential cohomology. It's an easy, I would say it's a pretty easy example, and it's a familiar one. Now, as in the case of ordinary differential cohomology, how much more information are we getting? So again, we'll look at pairs. It's an element of K and a differential form in wedge BL such that it's coherent. One is the form represents the Chern character of the element of K. And so we have a map of K hat onto that, and its kernel this time is the total odd cohomology with coefficients in C modulo the de Rham image of this wedge GL. This is also a lattice cohomologically, so it's a complex torus of the dimension of the sum as the odd Beatty numbers. It's not the same torus as it would be if these were just forms with integral periods or the real image of integral cohomology. It's a different torus, but it has the same dimension because this is a different lattice. So that's the additional information that this carries, a point on a torus. So now, two guys, Bunke and Stieck, have recently shown that the diagram, again, uniquely categorizes K hat. So going back a moment, they say, look, for even K, this is it. Anything that satisfies this diagram is isomorphic to, or naturally, there's a natural transformation of that to anything else. So as a functor, the diagram, in the case of even K, characterizes the functor. However, they also showed that the corresponding diagram for odd K theory does not so categorize the functor. So some additional axiom is required, some additional property of differential K theory in order that in full generality it's characterized by axioms is required besides just the diagram, because the odd K theory case should work as well. Now, what we did today was in the context of C mod Z. It was just simple, but we could just as well have worked in the framework of Hermitian vector bundles with connections that preserve the Hermitian structure. The only difference with the diagrams would be C would be replaced by R, and C mod Z would be replaced by R mod Z. So here's an interesting fact. Let's let K hat sub U be this unitary differential K theory. If X is a compact-oriented manifold, and I have some element of K of X, then I can find an element of K hat which gives you that bundle, or gives you that element of K with harmonic forms. So if you wanted to represent the Chern character by, you want a connection which gives harmonic forms, you can always find one. And in fact, the family of such guys, elements of Ku, is parameterized by that torus for some of the odd Beatty numbers. So, if X is 4 dimensions and has a finite fundamental group, this guy is unique. So that's a useful, I think that could be a useful thing. So the there are physicists in the audience who might be able to tell us why K hat may end up being useful. I was put onto it by Greg Moore, who was telling me at a rather boozy dinner that things like differential characters, the ordinary ones, were swell, but they didn't quite fit the bill. You really needed K-theory. So Dennis and I said, okay, we'll do one with K-theory, and tried to develop it for a while and came up with this construction. So, but I think that it is a good way of grouping, putting connections together, and there it is. So that's my talk on the roots of differential K-theory.